Hi, everybody. Thank you first for the invitation to do this talk today. I'm going to talk about the use of remote sensing data for quantifying desertification trends. So in this work, what I'm going to present actually was the result of a project, of a farmer project that we've done to the European Space Agency, which we had an objective which was to try to characterize certification susceptibility based mainly on remote sensing data. And not only remote sensing data, but with data that was freely available to anyone. Because many times we need to calculate, we need to map these indicators, and many times the resources are not available. So we made here an effort to do it without paying data. So we only use freely available data. And the objective of the index that we developed, which is here, in the middle, actually is contributing to the second objective of the UNCCD impact indicators, which is to improve the conditions of the ecosystems. And they are this indicator, although it does not correspond to any one of the indicators defined by the UNCCD, because they are not actually defined. They are in the process of definition. They contribute. It contributes to the. It's related with the Arity index, and it's also related with trends in. Sorry, I cannot read that. Trends in land cover, structure, and trends in land cover, productivity, and or functioning of the land. So our index that I'm going to explain is related to these three indexes. Oh, sorry. Okay. So how can our indicator contribute? So this indicator points out regions where land conditions are changing towards the occurrence of desertification processes. So this index does not point out the most desertified areas or less. They are pointing out to places which are in a changing process. And these are the ones where we can do some actions, we can do some preventive actions to combat this desertification. So our index has this dynamic view and intends to look at places that may change to a different stage or a different state. I think that you've been talking a little bit this before from the previous presentation, so this is not new. So in our cases, we define two fundamental steps. We define a step where we characterize the climate dynamics mainly through precipitation. So we know that many times desertification is associated with the shortage of water, and through biophysical factors trying to characterize vegetation and or soil, depending on the land cover status. And at the second space, we did the special characterization of this index, conditioned to this climate dynamics and to the vegetation and soil. And so these are the two basic steps of our index. So the framework of our proposed methodology was to characterize, to set up a set of climatic indicators through precipitation. And here in precipitation, we looked to a long series of precipitation data, and we tried to characterize not only the state, the status, but also the dynamic of this precipitation. And we used different indexes, and we used not only means, but also variances and slopes. We tried to look how this precipitation is changing depending on the susceptibility of desertification of each location that we were analyzing, and see how different they were. And simultaneously, we were characterizing the biophysics indicators through the analysis of remote sensing images. And now we are talking about remote sensing images of the, we are talking about images, I'm missing the word, images, you interrupted, I missed the word. Okay, I will talk later, sorry. But actually both factors or both indicators are based on remote sensing images, because the data that we used here for the climatic indicators was a data that was retrieved from Area Terrain archive, which is it's an archive of reanalysis of climatic data, and these Area Terrain are models that are done from remote sensing images, and then they are updated with real data from monitoring stations, from meteorological monitoring stations. So actually we are using remote sensing images for both type of factors in a different way. These ones we retrieved, they were already processed, okay? We didn't use the remote sensing image, we used the archive that resulted from these remote sensing images, and in this case we have processed all the images. And from these images, we calculate what we call vegetation indexes, and I'm going to explain a little bit about that. And also we calculated soil indexes to analyze the type of soils. And based on the relation between these two types of factors, we did some co-estimation. Prior we calculate the bivariate relations between the climate and the biophysics, and then we end with these desertification indexes. What we see here is that we also used globe cover land cover maps. Globe cover is a land cover map produced that covers the entire globe, because in this project we had the objective of applying this indicator to 3 areas of the globe: to Portugal, to Brazil, and to Mozambique. So we used a globe cover because this globe cover was the classes, the land cover classes were common to the 3 areas, which is a difficult thing to get. Okay, so explaining a little bit, I don't know how many of you knows what is remote sensing images. So I imagine that some of you will know, but some of you don't. So I'm going to explain very, very briefly. Actually, what we are doing, we know that objects at the surface reflect the energy that is emitted by the sun, and that the way that they reflect this light or this energy depends on the material that's on the surface. So what we get here on the sensors is the result of the energy reflected by the surface of the Earth, but also from all the interactions that are in the atmosphere. And so we have some information about the objects, but we have a lot of noise on these images. But still, they do have some information, and they allow us to distinguish different objects based on what we call the electromagnetic pattern, or the radiometric pattern of these objects. Just you to have an idea, these images that we used in this project we call optical images, because we have here the frequency of the electromagnetic spectrum, and you have here some interesting pictures that tells us the dimension of these electromagnetic waves. This is the energy that comes from the sun that is reflected and we get on the sensor. And what we measure is this energy that arrives on the sensor. And what we are using in these optical images is only a small part of the spectrum, which are the infrared and the visible mainly. Okay, so we are looking at this part of the spectrum of the electromagnetic spectrum. So what we register is what we get on the sensor, and what we see on the sensor is the result of the atmosphere and on the land surface. So we use what we call the meteorologic satellites to register images of the atmosphere, and based on these images, we do the meteorological models and we predict the meteorology. With other types of images, we can get the result of what we have on the surface. So why do we identify different objects on these images? Because they have different patterns, okay? This is the reflectivity of the reflectance. This is the wavelength and the reflectance. And we have used 3 examples of what we get when we are looking at the reflectance of water. So we have a very small reflectance. It's the object that looks like a black body on the surface. So it's the one that absorbs most of the energy, and it reflects very little energy, and only on the visible and near infrared. So we get a very different pattern when we look at the vegetation. We see that we have here absorption of the red and of the blue, and a reflectance here on the green, and we have a larger reflectance, and then we have a large reflectance on the near infrared. So we identify very easily the vegetation because it has a very different pattern from the other objects. Here we have the soil. The soil is more confused because it's not so. We have in the case of vegetation, it's much more easy and has a much more distinctive pattern. And we see also that in the soil is a little bit more confused. It reflects. It doesn't have so much characteristic pattern, okay? But still, we can very easily identify vegetation from the soil and from the water. And of course, this is a general plot, but we have different patterns for different types of vegetation, okay? And that's why we can identify different types of vegetation. Because our sensor is not going to measure all this, we are going to measure a part of these parts of this electromagnetic spectrum, and we will measure, for instance, here, and then we'll measure here, and then we'll measure here. So we will have like different slices of the electromagnetic spectrum. And because they have different reflections in different ranges, we will identify these objects. So that's how we do classification, and we obtain the land cover maps. Okay, so after this brief introduction to remote sensing, I'm going to talk a little bit of what we have done with the analysis that we have done with the climate data. So we used the European Center for Forecast archive, the Erentrine data archive, and we had about 20 years of data. Okay, 20 years of data of precipitation. And based on this, we calculated, we tried to calculate different parameters from this precipitation data, and we end up with this index, which is the number of days with precipitation under 1 millimeter during an hydrological year. So what this is giving us is the number of dry days during an entire year. And it's like a drought index, okay? It's like indicating us the places with more dry have more numbers of drought, a higher drought index. They will have more days per year of under 1 millimeter. And we analyzed this indicator over the 20 years, and we found out that we found out two components that we classified as static component and dynamic component. So the static component is based on the mean of this indicator over time. Okay, it gives us the mean images, the mean image or the mean drought of a certain place. And the dynamic component is based on the variance or the trend of the variance over time. It's looking at how the variance is changing over time. So, it's not moving. Let's see here. For instance, we have here an example This is Mozambique. This is the map of Mozambique. This was our, this was defined as our pilot area, but you can see here the entire country. And what we see here, if we look at these 20 years of this indicator, we'll see the red are the highest values and the blue are the lowest values. And we see that we have here the highest values of this drought index. It means that this area is more affected by drought over the years. However, if we look here at the variance, we see that some of the places are variable over the time. So we did this like doing windows, calculating the variance over the years, but with small windows that are moving. So we see here, in this case it's the general variance, sorry. So we see here that the variance is distinct. So our places where the mean is doesn't vary, so the index don't change much from year to year, but you see here places where it changes a lot. So we have one year of drought, and we have other years without drought. Okay, so we see we can combine these to understand well what is going on, and we can see this to all the three countries that we were analyzing. This is Portugal, Brazil, and Mozambique. We did the same exercise to all to the three countries. And we ended up with this conclusion that there was, of course, that the mean of the indicator gives us an idea of how dry is a certain location compared to others. So it gives us the relative dryness of the territory. But the variance over time gives us an idea how this drought or this dryness is changing over time. And what we found out was, we have in Portugal, I don't know if you know, but we have in the south, we have an area of high desertification with more arid, and also here in the north of the country, we have more arid. So the semi-arid of Portugal is located here and here. And what we concluded was something like this, that the variance was changing depending on the location, was changing depending on the aridity of the location. Okay, so these areas which are more susceptible, the variance was decreasing. And these places, the variance was increasing. And here in the middle, we had no changes in the variance. What does it mean, the change of the decrease of the variance? It means that the drought is becoming, because we are talking about places where we have more drought, is becoming more stable. Okay, we will have more. We will have drought, so it's not changing. The indicator is not changing, so the drought is becoming more persistent. Okay, that's what it indicates. We've done this to the three countries, and we got the same conclusion. So we accepted this, that we had a static component that was based on this mean of the drought indicator, and we have the change, a dynamic component, which was built on the slope of that trend of the drought indicator. So we're saying that the places that are becoming more stable in terms of drought indicator, and those which have higher drought indicators are more susceptible when we look related with the shortage of water. Of course, I'm not talking about other factors. I'm only talking about shortage of water. Okay, so this was the climate, and also we can see here, for instance, the example of Mozambique. Mozambique is here, and we enlarged the area because we found out we were interested to see how it was if we looked around. And here is the map of the static component. These are large pixels because these are the data from area terrain. Okay, so they represent large areas. And we see here, for instance, that this area here, in terms of more, let's see if I have another. Okay, let's see this one because it's more interesting. When we look here at these two maps, we see the temporal trend and the long temporal trend. So this is the static, and this is the static, and this is the dynamic component. And what we see here, if you look at the static, this is the area, this is the driest area, which is the desert here, okay? But when we look at the dynamic, we see that this is not the place where it's changing, because the desert is not going to change. It's not going to revert or change to other things. So it's already desertified. So when you look at here, we see that this area is the area that is more susceptible to change the status, okay, in terms of drought. So I would say that this is not very. This is very different from what I have in my computer. The colors are not very good here, but what I tell you is that you should see here like orange, okay, that you don't see. I'm sorry, but what I'm saying is, although this is, in terms of dry, this is the driest part, it's not the ones that we are concerned about. We are more concerned about these ones which are not desertified yet, and that will appear here as the more susceptible in terms of climate. So what we did next, so this is the area that can change, turning drier. So what we've done next, we related this drought index and these two components, the static and the dynamic component, with vegetation indexes calculated from the remote sensing images. So the vegetation index that we calculated was the MDVI, but just going through this, then plants absorb radiation in the blue and red regions of the electromagnetic spectrum, and they reflect in the near infrared. So what we do, we use these two regions to calculate this vegetation index. And actually what we see is that when we use we calculate these relations that are based in these channels, the red and near infrared, we can see the vegetation as a whole, okay, and it's a proxy of the productivity, okay. So it depends not only on the quantity of vegetation present, but also on the productivity of this vegetation. So it's not an easy index to do the interpretation. It's not easy because it depends on both things. So it's a balance between the quantity of vegetation present and the productivity of this vegetation. If we have a lot of vegetation with a lot of water and high productivity, we'll have a very high NDVI. If you have few vegetation, low productivity, you will have low NDVIs. And NDVI, because it's normalized, it varies between -1 and 1. And if it's vegetation, it will be between 0 and 1. So we will have these two things. So we try to relate this vegetation. Just here an example of this is Landsat images that we used for doing this work, because Landsat images, for two reasons, because it's the longest series of remote sensing images that we have on Earth of land surface. And also we needed to have long time series of images, but also because they are freely available to download to anyone which are interested. So it's a public archive of what is happening on Earth for the last 20 years. So if we look at these images. This is the near infrared, and this is the red. So you see the brightest points are vegetation, because they are the vegetation is highly reflective in the near infrared, and is absorbed in the red. So the dark shades are the vegetation. So they appeared very dark in red and very bright in near infrared. And this is a combination of red, near infrared, and green. So it's what we call a color composite, a false color composite. So it's not a true color, because we only see with our eyes the blue, the green, and the red. Okay, that's all our eyes can see. But we can do this false color composite using other ranges of the electromagnetic spectrum.